Hi ladies and gentlemen, so today we're taking a look at part 1 of 5.4 rational functions. So the objective for today is to identify zeros and asymptotes of rational functions when they're in a specific form. So there are two types of rational functions, or two ways rational functions could be written. The first is in the form of f of x equals a divided by x minus h plus k, where we have this constant number k added or subtracted on the end of the fraction, or after the fraction. The other type of rational function is like in this second box where we have p of x divided by q of x. So we have one great big fraction with the two polynomials being divided. What we're going to focus on in the part 1 of 5.4's lesson are rational functions that are in this first form. And what we're going to do is we're going to focus on identifying key features of these graphs in order to graph them on grid paper without the use of a graphing calculator. So the first way we do that is we identify what's called a vertical asymptote, so a vertical line that divides our graph up. And the vertical asymptote is always at the line of x equals h. So looking at that denominator and solving it for x will give you the value of which creates a vertical asymptote. That also gives us our restriction on our domain, which we've talked about already because we're not allowed to divide by 0, so the asymptote is created by whatever value would give us 0 in our denominator of our fraction, and then that also gives us our domain restriction. Then we have what's called a horizontal asymptote. And a horizontal asymptote is at the line y equals k. So the horizontal asymptote comes from the value that's being added or subtracted after the fraction. So let's put this to practice through a couple of example problems. So example 1, identify the asymptote's domain and range of the function g of x equals 1 divided by x plus 5 and then all minus 4. So what we're going to do here is we can recognize that we are not allowed to divide by 0. So if we take this denominator and solve it for x by subtracting 5 over, so I set it equal to 0, I subtract 5, and I get negative 5. What that's doing for me is it's identifying what's called the vertical asymptote. Right? And the vertical asymptote then is at the line x equals negative 5. Here, let me move this over a little bit so you can see better. There we go. Then we can identify our horizontal asymptote. The horizontal asymptote always occurs, here we go, changing colors. Horizontal asymptote always occurs at y equals whatever this k value is, or the constant number is added on the end, so that would be negative 4. So we find the vertical asymptote by taking the denominator, solving it for x. We find the horizontal asymptote by taking the number on the end of the fraction. Then, to identify our domain and range here, the domain is going to be all real numbers, but with the exception of this vertical asymptote. So we say all real numbers except x is not allowed to be negative 5. And then the range works very similarly with the horizontal asymptote. It is also all real numbers except y can't equal negative 4. And that's because these asymptotes are these voids in the graph where there's no actual value located, and that's why there's an asymptote there. So whenever you have an asymptote, you have a restriction on either your domain and range, depending on what value there's an asymptote at. All right, so now I'll have you guys work on example 2. So example 2, you should hopefully have given this a try on your own first, identifying the asymptote's domain and range. We have a vertical asymptote and a horizontal asymptote. Know that when you're defining the vertical asymptotes and the horizontal asymptotes, you need to make sure that you're defining them in terms of x equals and y equals. If you just write the number or don't say x equals or y equals or flip-flops them, that's technically incorrect because we're defining a line here. So the vertical asymptote is by looking at that denominator, solving it for x. My denominator is x minus 7, so if I solve that for x, I would get x is equal to a positive 7. The horizontal asymptote is looking at the number added or subtracted on the end, which in this case is negative 2, so the horizontal asymptote is y equals negative 2. My domain, which I wrote kind of big here, so let me minimize that a bit. All right, my domain is all real numbers except where that vertical asymptote exists. So a more mathy way you could write this is you could say x is an element of all real numbers, except x is not allowed to equal 7. Again, this is a really mathy way of writing it. For just regular Algebra 2, it is not a requirement to write it this way, but if you were to move into Trig and Pre-Calc or Honors Algebra 2 or Honors Trig and Pre-Calc, you would want to write it more formally like I have it written here. Range. We say y is an element of all real numbers, which just means y can be any number, except y is not allowed to be negative 2. All right, so what we've talked about so far is identifying vertical and horizontal asymptotes for rational functions that are in this form. What we're going to talk about next is the second box from the beginning of this lesson, where it's zeros and vertical asymptotes of rational functions that are now in this second form, where you have p of x divided by q of x. So your zeros of each real value are always looking at the numerator and solving it for x, and that's because with fractions, 0 divided by any number is always 0. So we don't have to set the whole fraction equal to 0, we just have to set the numerator equal to 0 to figure out where it crosses the x-axis. Finding vertical asymptotes is taking that denominator and solving it for x, because that's going to give us those restrictions on values we can plug in, because that's where the denominator would be 0, which is not okay, and that's how we find the vertical asymptotes. So let's put this to practice now when looking at example 3. So the first thing we need to do, though, is factor. That's always going to set us up for the most success, is to get everything in factored form. So when looking at this, I'm thinking about what is the factored form of x squared plus 2x minus 15, and the numbers that multiply to negative 15 but add to 2 are positive 5 and minus 3. What I'm going to do from here is I'm going to use this factored form now to help me find my zeros and my vertical asymptotes. So again, the zeros are coming from taking this numerator, setting it equal to 0, and solving for x, and that's going to tell me where my graph crosses the x-axis, because again, it crosses the x-axis when the y value is 0, and a fraction equals 0 every time its numerator is 0. So we don't have to set the whole fraction equal to 0, we just have to set the top of it to figure out where it crosses the x-axis. And it's nice that this is in factored form, because then I can easily set my first factored piece of x plus 5 equal to 0 and get an answer of x equals negative 5. Then I can set the second factor piece of x minus 3 equal to 0 and get x equals 3. So I have my two zeros at negative 5 and 3. Then we can find the vertical asymptotes. And there's only one here, because that's taking our denominator of this fraction, which is x minus 1, and solving it for x, so we would get a vertical asymptote at x equals positive 1. All right, so now I want you to take a moment and try example 4 on your own. Press play when you're ready to see the answer. All right, so the first thing you should have done is factor the numerator. X squared minus 9x plus 14 factors into x minus 7 and x minus 2. And then we have x plus 5 in our denominator. Our zeros, when we go to solve the numerator for x, I would get 7 and 2. And again, that's by solving that numerator for x once it's in the factored form. And then my vertical asymptotes, which is solving the denominator for x, would be -5. All right, so that wraps up part 1 of the 5.4 lesson. Next, we'll learn the part 2 of this lesson. Thank you so much.